Okay, let's start. Good morning. So today, this week is a week for our second midterm. So today and tomorrow we're going to be covering topics that are technically included in the second midterm, but certainly, given that we have already covered so much stuff, it would be perhaps unfair and perhaps cruel to require that you guys understand and digest all this stuff that we're going to discuss this week. In any event, I want to keep working on this implicit function theorem. I'm going to discuss this underlying principle that I mentioned that is rather more general. Probably what we're going to do is we're not going to prove this, but at the very least you should have an understanding as to what it says. Probably I might put items or elements related to this stuff in the next problem set. Okay. So I'm going to be taking attendance today. And of course, this week is the week of Halloween, so we have candy. If you have dietary restrictions, this one is for you, okay? If you're vegan or if you have allergies, go for this one. Otherwise, you're on your own, okay? And let's start it here. There you go. Take as many as you want because I'm going to bring this tomorrow and then the day after, and then probably if there's any more candy left on Friday also, take many, okay? I don't want that near me for obvious reasons. Before I start, are there any comments or questions? I realize perhaps, oh, there's a spider. I realize perhaps that the last problem set was kind of rough, the polynomials and stuff. Yeah. Yeah. Ultimately, you know, we don't grade your work based on how accurate you are often. And specifically for this problem set, I think the main idea that I was hoping you guys would get was that, you know, just like you're happy with polynomial functions in one variable, in multivariable too, that's sort of like the ground truth in a sense. There are still polynomial functions that you can define, and they are again the nice functions. Okay, that's all you need. And anyway, I think I'm going to be doing problem set 3 I'm going to solve problem set 3 in the selected solutions. Yesterday I spent a couple hours sort of computing things. It was so pleasant for me, but it's so nice. Calculus, you know, it's like, for a professional mathematician such as myself, like cutting edge math is not this pleasant. I'll tell you, it's like everything has like 5 different clauses, and like you have to be super careful with everything. Now I can understand, since you're learning these things now, it might, you know, feel like this as opposed to 2 plus 2 equals 4. But I'll tell you, it's like it is pleasant. Calculus, when it works, it works beautifully and it's pleasant. Anyway. So this is the background machinery, Banach Contraction Principle. And then there's a second version of that, which really is what we're going to use. I didn't even finish stating this. So maybe even before restating the implicit function theorem, let me go over what this actually says, okay? Let's just focus on BCP1. Both BCP1 and BCP2, they have nothing to do with differential calculus. And if you look at the schedule on the syllabus, I was hoping to cover these when we were discussing metric spaces, but I ended up sort of cutting it out because it wasn't necessary at the time. And ultimately, this is like Banach Contraction Principle is one of the 3 fundamental theorems about metric spaces, okay? So BCP is the first one or 2, whatever. Second one is, well, it's basically something that allows you to do Bolzano-Weierstrass for sequences of functions. That is what is called Arzela-Ascoli theorem. And then the third one is what is called Baire Category theorem, which allows you to make sense of the following statement. You will say, I have this property, but I want this property to be satisfied typically. So maybe it's not satisfied for all such functions or all functions, whatever, but for most functions it is satisfied. And so Baire Category theorem, this third theorem in the theory of metric spaces, allow you to make rigorous or precise sense of this. So we're not going to cover all three of these, and probably we're not even going to cover this, BCP, in class. But this is something we're going to use. And it says the following, okay? Just going back to this world of metric spaces, continuity, all that stuff. Focusing on BCP1, if you have a metric space X and a function capital K from X to itself, assuming that your metric space is complete, in other words, any Cauchy sequence in X has a limit, right? That was the definition of completeness. And furthermore, if the Lipschitz constant of K is less than 1, so think of Lipschitz constant, we had defined this before. It's basically something like an operator norm. Let me remind you. This is basically the rise over run, right? So, but I want to state it in the context of metric spaces. So I'm going to feed 2 points into K. So this is my rise, divided by the distance between the inputs. And I'm going to take the soup over these. But in order for this to make sense, I need X to be not equal to Y. This is one way of defining the Lipschitz constant. It's basically the operator norm. And indeed, if K is a linear map, and if X is a norm space, Lipschitz constant is equal to the operator norm, okay? It's just that this is a nonlinear version that applies for arbitrary functions. Now, saying that the Lipschitz constant is less than 1 means that if you were to feed 2 points into your function and push them, right, if you were to look at their images, under K, they would get closer. If this is X, this is Y. Let's say that K of X went there. What this says is that compared to the initial distance, right, so this is the initial distance, when I apply K to both this and this, their distance has to shrink. Okay. And this is why I'm using the capital letter K, K for contraction. You usually write it with a C, but so contraction. Okay. Assuming these, BCP1 guarantees that in fact there's a unique, what is called fixed point of K. There's a unique point X star such that when you apply K to it, it stays where it is. I hope you, at least from an intuitive point of view, this makes sense, because assuming that the Lipschitz constant is less than 1 means that K shrinks the whole space into one thing. It's like a funnel. You take a limit somehow, and in the limit, you're going to have 1 point. Okay, that's all there is to it, really. Yes?
It's like the Brouwer's fixed point theorem. Like
This is much more general and more elementary. If there's time at the end of this class, what we're gonna do is, when we start talking about fundamental theorem of calculus, that is to say, Stokes' theorem, we're gonna figure out, if you have time, a more sort of sophisticated fixed point theorem, which is what your colleague is suggesting, using differential calculus. So it turns out that if you develop differential calculus enough, or integral calculus, whatever, you can go back and do topological stuff on top of that. So, but we'll get there later. The reason why I'm not covering the proof of this is not because it's complicated, okay? And I can even tell you the proof of this, ultimately. The proof of it is like this. You look at this idea. You say, take an initial condition x, define a sequence by saying x0 is x, and xn is k applied to xn minus 1. So you take an initial condition, x, let's say, keep iterating k. You apply, so k of x, k of x, and so on. You show that this sequence is Cauchy by your completeness assumption, it has to converge. This is the limit. That's the proof of it. It's not complicated, ultimately. But it takes time to write it out, and that's why I'm not going to write it. Any questions about what BCP1 says? From a graphical point of view, you could imagine this to be like this. Somehow, because k goes from x to x, imagine the horizontal is x, vertical x also is x also. And so you draw the graph of k. It says that the graph of k intersects this diagonal line at exactly one point. Maybe here. It cannot cross multiple times. From a sort of graphical point of view, that's what it says. Questions or comments? Now, BCP2 is essentially a souped-up version of BCP1. Or maybe even before going into this, let me just abbreviate this by saying, on complete metric spaces, contractions have unique fixed points. So that's how we can abbreviate this. Incomplete metric spaces, perhaps, or completeness implies as faster. Completeness implies contraction has unique fixed points. That's what BCP1 says. BCP2 essentially says the same thing, except that this time, instead of having one function, k, you have a family of functions. This family is parameterized by this other metric space. So, and then also, instead of assuming that k is defined everywhere, you say, let's let k to be defined on this open ball. Okay? Your assumptions are, so you see, when I write it like this, this means that this is k sub bullet. It goes from S into the space of functions from the ball into X. Right? Using this currying, you can sort of write it in other ways as well, but never mind. So if I were to plug in a lowercase s, that's a parameter, now I have k sub s. That's a function from this ball into X. The assumptions are, again, if X is complete, if the Lipschitz constant, sort of the uniform Lipschitz constant, you see I look at the Lipschitz constant of each of these functions, and then I look at the soup over all parameters, I want them to stay away from 1. It's some number lambda. This should be lambda. Third assumption, if instead of fixing s, if I were to fix the x value, I want continuity. That is to say, I want this k to be a family of, or continuously parameterized family of functions. Okay? I want continuous dependence on the parameter. And furthermore, finally, I want each of these functions to not move the center of the ball, x0, not more than some number, okay, some estimate. It doesn't really matter. I don't want k sub s to move the center of this ball too much. Then, these are the hypotheses, then it says, based on the BCP, we have a unique fixed point. But now for each s, I have a fixed point for k sub s. So I have a function of s. That's a unique function. And furthermore, it is continuous and so on. Then there is a unique function phi from s into x, such that for any s in s, phi of s is going to be the fixed point of k sub s. That is to say, k sub s applied to phi of s is phi of s. Furthermore, phi is continuous. Okay. Okay. And in fact, I have some estimates as well. Let me write it here. So this is one. Another one is for any s and for any x, phi of s is the limit as n goes to infinity of this. So this means that I'm taking x, like I said before, and I fixed an s. I keep iterating k sub s. And when I keep iterating, this converges to this point. And I have also estimates as to the distances. You want to say not only that this sequence converges, but you also want to say something about what is the convergence rate. For instance, it says that this is lambda to the n divided by 1 minus lambda times this. There's more estimates too, but let's not write these down. What does this mean, ultimately? Again, the summary is that in a complete metric space, you have unique fixed points for contractions. And furthermore, the unique fixed point depends continuously on the function. That's how we can sort of keep this in mind. So contractions have unique fixed points. And the fixed point depends continuously on the function. Okay. Don't worry too much about the statement right now. The green parts are sufficient for us. Okay. The point of all this is that once you have these assumptions, completeness and contraction, then you have a unique fixed point for the function. And in fact, you have an algorithm. Okay. You can start with any initial condition and keep iterating your contraction. And eventually, you're going to converge exponentially fast to the solution you want. Any questions about this? I know this has been rather fast. But we're going to sort of use it in the implicit function theorem. By the way, for those of you who came in late, there's some candy going around. Should keep moving. And also, there's like, so if you're vegan or if you have allergies, take the stuff in the bag. Okay. Yeah, keep rotating. I don't want to take this back, okay? I want you to finish it. Okay. Last Saturday, I carved my first pumpkin, actually. My wife is, she's an artist, and she knows how to instruct people like me. So I am confused how this is done. But anyway, it's pleasant. Anyway, so now that we have this in the background, let's try to see how we could use this to get the implicit function theorem. Let me remind you the statement. I'm not going to write down the problem. As usual, we have the standing assumption of M, a subset in E, and a subset in F. These are open subsets. E and F are normed spaces. But remember, for implicit function theorem and inverse function theorem, this is not enough. We're going to have to assume something more, because ultimately we're going to use BCP. BCP requires completeness. Therefore, we're going to require completeness for these. Okay, so far we haven't been requiring that. For inverse function theorem or implicit function theorem, you do need completeness. Not as much as I stated, but still somewhere you need it. Implicit function theorems. And again, remember from last week, we have two theorems, implicit function theorem, inverse function theorem. We showed, or I at least gave you some idea as to how these two statements are really equivalent. And in the textbook, when you look at it, they prove inverse function theorem and then derive implicit function theorem from that. I'm going to do it the other way around. And furthermore, I'm going to use a different method. This is such an important problem, the problem that this solves, that there are many different proofs. I like this proof more because ultimately it uses something, okay, this BCP stuff, that gives you an algorithm that converges to the phi that you want exponentially fast. That's why I like it. But the problem is, if this lambda is too close to 1, then the convergence is very slow. Okay? So we're sort of discussing this from a more pure point of view, but you can imagine how, for things like numerical analysis, convergence rates is an important thing. OK, implicit function theorem. Let's remind ourselves. Let k be a positive integer or infinity. This is going to be our regularity for the function. E be a product space, E1 times E2. M2, let's say, is a product neighborhood or product open set. Let's let F to be a ck function from M to N. And X be an input point. So a point in M. If E and F are complete, and remember this point of Banach space, same Banach, he basically sort of proved this in his PhD thesis, and he was also interested in using this in the context of vector spaces or norm spaces. That's why Banach spaces are called Banach now. So if E and F are complete, and furthermore, the second partial of this function is invertible, right? That was the assumption. If complete and d2f at x is invertible. And when I say invertible, I mean the inverse has to exist as a linear transformation, but furthermore, it has to exist as a bounded linear transformation. I want the operator bound of the inverse to be finite also. With bounded linear then, right, this second partial being invertible was the necessary condition for the implicit function problem for the theorem. We were just saying necessary condition is sufficient, assuming completeness. Okay? Then there is an open set, M1 tilde, that contains x1, and a unique function phi from M1 tilde to M2. And this is also ck, as regular as the original function, f, such that, well, it fits the initial data. That is to say, phi of x1 equals x2. And furthermore, for any x1 bar in M1 tilde, if I were to feed x1 bar together with phi of x1 bar, it is in the same level set as the initial condition. This is the statement. I had written this before. I just wrote it again. So here's the idea of the proof. Okay? We have like 20 minutes. I'm going to write down the idea of the proof first, certain steps, and depending on how much time we have left, I'm going to go into detail. Essentially, first you look at this higher order regularity. Okay? Even though, in principle, if I start with, let's say, a twice continuously differentiable function f, my solution should be also twice continuously differentiable. When you look at this, the condition that is given here, the assumptions, are of first order. I'm assuming specific things only about the first order infinitesimals. And so instead of focusing on higher order derivatives, I'm just going to say, oh, let me first try to come up with a function that is once continuously differentiable. And then you say, even before that, maybe if I can show that phi is, there's a phi, and it is continuous, maybe I can upgrade it. So this is what is called bootstrapping. You say, I'm just going to, instead of going ck, I'm going to go for c0. And then I'm going to sort of try to upgrade my function. Okay? Step one. Step one. And now that I wrote BCP up there, somehow you should expect that there is a function, k, like above, parameterized by the first value, first argument. And you would want this guy to be the unique fixed point. Okay? So first of all, what I'm going to do is I'm going to try to rewrite this, what I'm trying to do, in terms of a certain family of functions so that I can apply BCP. And this is really one of the perhaps harder parts of BCP stuff. Even though it might look scary, ultimately the methods to prove these statements are elementary. What is often a challenge is to figure out to what you're going to apply this. So what is the k in this situation? That's the problem. That requires some artistry, if anything. So, step one. Define a function k that's going to go from m1 times m2 into m2. Okay? And how is this defined? It's defined like so. You feed to it x1 and x2, well, these are fixed, x1 bar and x2 bar, these are not fixed now, and send it to this. Okay, so this x is x1, x2 that is given, that is the given initial condition. That x is this x. x1 bar, x2 bar, you should think of it as a perturbation. Now, why would I look at this function? Because you see, the solution that I want within the paradigm of the implicit function theorem becomes a fixed point for this function. So you remember last week we were taking implicit function problem, turning it into the inverse function problem whatsoever. Again, we're now switching paradigms. I took something from differential calculus and I'm sort of rephrasing things in terms of the paradigm of BCP. Here's what I mean. This is what I want. If this is equal to this, their difference is 0, which means that in K, this is going to be 0. Okay, so let me write it perhaps. Okay. Phi is something I want, right? It solves this problem. If and only if the difference is 0. If and only if, well, if this vector is 0, if I were to apply a linear transformation to it, it's still going to be 0. And this is going to be equal to x2 bar. But then this means, and of course, x2 bar should be phi of x1 bar. This means, because this side is K, now, instead of writing it like this, I could have written it so that this first argument is sort of like a subscript. So perhaps it's better to write it like so. Okay. That's what I want. You see? Let me perhaps pull it like this. All this is to say, pull this way as well so that you can see. I start with this, and I'm trying to rephrase things so that it fits into the BCP paradigm. So I start with the equation I'm trying to solve, and I rewrite it in such a way that it's the fixed point of something. Okay, now this is a fixed point equation. Then you say, oh, if I could verify that the conditions of BCP2 are satisfied, BCP2 automatically gives me that there's a unique phi. Does this make sense? This is an important point. So here, the parameter S in BCP would be x1 bar. And that's it, yeah. So this is for S equals x1 bar. questions, comments? I feel like I'm losing you. Ask questions. Yeah.
So you said BCP gives us that there exists a unique like inverse function of phi. So like, or is that what you meant by that, or?
Yeah, that was the step one. Okay.
Yeah.
Step one is defining this function. You're going ahead, but ultimately yes, I'm defining this k. Step one is to define it and verify that it satisfies the assumptions of BCP2. That's the first step. But even before that, I want you to understand why I'm looking at this specific function. Because often when you read proofs and stuff, they just say, look at this function and do things with it. But I want you to understand why you're looking at this function. I look at BCP, even though the assumptions are kind of dubious at this point, it's not clear. There is a family of functions, right? It is parameterized by something, and it is defined on a metric space. In this case, it's even more than a metric space, but never mind, okay? What is important is the equation that you're trying to solve, the implicit function problem, in terms of this k, is a fixed point problem. Okay. So let me concatenate this. By just saying that then let's say this is equal to f of x if and only if k sub x1 bar applied to phi of x1 bar equals phi of x1 bar. So the problem that we want to solve is a fixed point problem in terms of k. It's a fixed point problem. Okay. And like I said, after your colleague suggested, next part in step one, maybe we should call it step two, is to verify that this k satisfies the hypotheses of BCP2. What does it mean? Well, it means that we need to figure out what this R and so on. So we're not going to apply BCP2 exactly to this function, but we're going to restrict the domain, okay? Let me just say k fits into BCP2, okay? So we're not going to consider k on this full open subset, but we're going to look at certain balls near the initial condition x1, x2. And that's where we use this assumption that D2F is invertible. After you verify that this satisfies BCP2, well, BCP2 guarantees that you have a unique solution. So BCP2, there's a unique function, phi. Let me just say it like this. S, an open ball around x1. So part of figuring this step 2 is to figure out what is the radius of this open ball, for instance. This is, and then by applying BCP2, we have that there's a unique function that goes from this open ball S into the second component. That satisfies, that solves. This. And furthermore, again by BCP2, this function is automatically continuous. Phi not only exists, but in fact it is a continuous function. So at this stage, we have a continuous solution for our implicit function problem. And again, purely based on this BCP stuff, you have ways to estimate what the formula for this is. Okay? You just feed it to this function, you keep iterating. I'll say a couple words about what that means in a second. And finally, step 3 is, well, to figure out that this function, in fact, has to be differentiable. Once you have a function, you want to show that it is continuous. Once you have a continuous function, you want to show that it is more than continuous, maybe C1. Once you have C1, you want to show that it's C2 and so on. Step 3, phi is C1. Step 4, phi is CK. I hope at this stage you could believe me if I were to say, once you're at C1, going to CK is just induction. So going from here to there, it's a matter of sort of technicality typically, but it's essentially induction on the regularity. Okay. Step 1 is nothing but restating something. Step 2 is where you have some technicality, verification of this function fitting into BCP2. This requires some considerations, some essentially mean value theorem type stuff. Okay. So I think I want to discuss this part. I want to assume we're at the end of step 2. We have a continuous function. And I want to show how we can verify that, in fact, this function would need to be C1 now. I'm going to leave this part to you, actually, CK. Step 4 is yours, because that's essentially induction. I want to go from step 2 to step 3. Let's just black box this BCP stuff. Let's assume it works. Let's also assume furthermore that we can sort of figure out an open ball, S, so that it fits into BCP2, and we have a continuous function defined. I think I'm going to write it here. Yeah, so for instance, in the statement of the implicit function theorem, this open set M1 tilde that contains x1 is going to be exactly the same thing as this open ball here. Okay. I have at this stage, at the end of step 2, a continuous solution to my implicit function problem. Okay? Because in step 1, we verified that the fixed point for k is the same thing as a solution to the implicit function problem. At the end of step 2, I have a continuous solution. Solution. This means that in terms of the original function f, I have this. I want to show that phi is differentiable. I want to start. I have 2 minutes. Let me just write what I want to show. I don't think we're going to have enough time. Tomorrow I'm going to spend some time, and then we're going to switch over to integral calculus. What I want is to show that this guy is, what was the equation? It was this. The point is that I have a candidate for what the derivative ought to be. All I need to do then is to take this operator, put it into the limit, and show that the limit goes to 0. That's what I'm going to do to show that phi is differentiable. I have a candidate for the limit, for the derivative. I'm just going to use a candidate and show that it actually fits. Okay. I think that's all for today. Thank you. I'll see you tomorrow. Yeah, I think it's time to stop. Start. Good morning. So today, I want to say a couple more words about this implicit function theorem. I want to finish the proof of this, one of these steps. Remember, we were discussing the proof of the implicit function theorem. I told you that first, using BCP stuff, Banach Contraction Principle stuff, you come up with a continuous solution to the problem. Then, by some argument, you show that it is continuously differentiable. And then the next step was, once you have C1, you show that it is C infinity or CK, whatever. And so I just want to discuss how we can establish this step. Then I'd like to say a couple words about what really is going on underneath. I would like to draw some graphs, some pictures, and see what more can be said. And then once we do these things, I want to say a couple words about integration. And next week we're going to be spending on integration. We'll see. Okay. So remember the implicit function problem. Essentially, the idea was you have a function like this, and you have a fixed point with components x1 and x2, and this product open set. And the assumption was that the vertical partial, so the second partial, at this given point is invertible. And what we wanted to do is, well, we wanted to write the second component as a function of the first component, at least near this initial condition. So we wanted an open set inside the first component that contains x1. Oh, you don't need to bring it back. You can just just keep rotating. Yeah. We wanted an open set around x1 and a function phi that goes from this open set into the second component, such that if I were to take an x1 bar in this open set, so it's a perturbation of the initial condition, and pair it with the image, so the output under this function phi, I want this to be in the same level set, same height. That was the need. That was what we were trying to do. And I told you that somehow we have this machinery, Banach Contraction Principle, that you can use by basically looking at this function. We define this k function. We said, oh, this is a contraction. You can show this. And then BCP tells you that for any x1 bar, this is a unique fixed point, and that fixed point is going to be phi of x1 bar. I'm going to draw a picture as to what that means in a second. For now, let's just focus on this. Somehow we have this function. And at this stage, I'm saying, let's assume that this is only continuous. So you only have continuous dependence of the second coordinate on the first coordinate. I want to show that it is, in fact, differentiable, this dependency. And so we have a candidate for what the derivative ought to be. And so we can sort of write down the limit and show that it is 0. Or we can sort of do this little o stuff. And in fact, that's what I'm going to do. Slightly easier, I think. And so here's a proof. This is this fixed height. Right? This is my initial condition. This is the height at the initial condition. Now, if I were to perturb x1 by some small amount, because I know that phi is a solution to the implicit function problem, if I were to look at this, this would be, again, still equal to the same height. Okay? Now, what I want to do is this. Instead of phi of x1 plus h1, I want to have phi of x1 plus maybe h2. And in fact, instead of writing it like this, I can perturb a perturbation. OK. And so then I have this. OK. This is if you want the 0th order Taylor approximation. Because if phi is C0, 0th order Taylor approximation works, which means that this is equal to the 0th order Taylor polynomial, which is just a constant, of course, plus higher order terms. Higher order terms in this case means anything that is faster than h1 in norm to the 0. Right? So the regularity goes to the exponents, and h in norm to the 0 is just little o of 1. This, of course, means nothing but as h1 goes to 0, this converges to this. This is just equivalent to continuity. And so what I'm going to do is I'm going to denote the difference of these two by h2. So that h2 is little o of 1 as h1 goes to 0. This means that h2 is a perturbation that goes to 0 as h1 goes to 0. OK. And so with this, then I can write phi of x1 bar plus h1 to be phi of x1 bar plus h2. But now, to this I can apply, so this f, I can apply the Taylor approximation if you want, or just use the fact that f is differentiable, and expand this. So it's this, plus the first derivative applied to h1, h2, but I can write it in terms of its components, and I can write it like so. d1f at x1 bar phi of x1 bar applied to h plus d2f x1 bar phi of x1 bar applied to h2 plus higher order terms in h1, h2. Little o of h1, h2, like so, as h1, h2 goes to 0. Now there are some cancellations, because again, by the fact that phi is a solution to the implicit function problem, this is equal to this. So this cancels out with this, and I have nothing but 0 equals this plus this plus this. OK. I'm going to continue there. So from here, and in fact, what I can do is I can solve for h2, because I know that this, by hypothesis, is invertible. Technically, this is, at this stage, maybe requires some comment as to why this is invertible. Well, you can just say that because f is c1, its derivative is c0, which means that nearby, so for a perturbation, this is going to be invertible also. You can say it that way. It's not that important at this stage, because I'm just trying to give you an idea. In any event, you can solve this for h2, but maybe I'll just take my time and write it like so. This is the first part. And then this is the second part. And then little o of h1, h2. That's what I said. And now I want to solve for this guy. Solving for h2 gives me that, right? So I need to apply the inverse of this to everything. That's not going to affect little o, because this is bounded linear. That's fine. This is going to turn into the inverse of this applied to this. But then if I'm solving for this guy, I'm going to have a minus also. So I'm going to have minus d2f x1 bar, phi of x1 bar, inverse d1f x1 bar, phi of x1 bar, applied to h1, and this. Now, perhaps the arcane thing here is that because h2 is little o of 1 as h1 goes to 0, in fact, little o of h1, h2 is also little o of h1. And furthermore, h2 is nothing but this difference, which means that solving for this part, I have the requirement. Minus d2f like this, e1f x1 bar, phi of x1 bar, like the h1 plus higher order terms. In other words, this bounded linear operator does fit into the first order Taylor approximation for phi near x1 bar. That is to say, it has to be the derivative, and phi has to be differentiable. And phi is differentiable. Okay, this shows that if you have a continuous solution to the implicit function problem, then that solution is differentiable, in fact, with this specific formula for the derivative. But furthermore, you can say, once you have this formula, well, if f is ck, its first partials are going to be ck minus 1. And taking the inverse of an operator, you showed, is infinitely differentiable. So you can see that this, that is to say, the derivative of phi is the composition of one c infinity function, one ck minus 1 function, one ck minus 1 function. When you compose these, you're going to get a ck minus 1 function, which means that phi has to be ck. And that's how we show ckness. Where is the induction in this step 4? Well, under the composition, you need to sort of argue just a little bit that indeed the composition of ck functions is ck. So that's the induction part. Okay, exercise. If AB are ck, then so is, well, then B composed with A is also ck. This requires induction. But if you have this, having this formula does give you that phi has to be as regular as f. Okay, this is the argument. I would recommend that you, instead of writing this little old stuff, just take this bounded linear operator, put it into the limit that supposedly defines differentiability, and show that that limit is 0. Essentially, you're going to argue the same thing, actually, because these are supposed to be the same things. OK. So that's that. Any questions or comments about this? Now, perhaps more important than the proof, the actual proof of implicit function theorem, is perhaps this idea underneath it, which is this setting up the k function. Right? So we defined this k function yesterday, and I told you, you show somehow that this fits into the paradigm of the Banach Contraction Principle, which in particular means that it's a contraction. And then you iterate it, I said. And then once you iterate it, it gives you the correct solution, the unique solution. So here's what I mean by this. Now I'm just going to draw a picture as to tell you what this is actually doing. Let's draw our usual picture. I have here, this time, a product neighborhood, which in this caricature world, I'm just going to draw as a rectangle. Let me draw it larger. OK, so this is E1, horizontal component. This is E2, the vertical component. So this is M. The shadow in the horizontal component is M1. So this is M1. And the vertical shadow is M2. I have a function that goes from M into something in this other space. OK? Now I need a couple points. I have the initial point, right, x1, comma x2. OK. So let's say x1, comma x2 is here. OK, this is my initial point x. It has its horizontal component, which is x1, and it has its vertical component, which is x2. Now x1 bar is going to be a small perturbation of x1. So maybe it's somewhere here. Okay, this is x1 bar. Oh, another thing I do, of course, maybe I should have used a color here too, but never mind. Once I have my initial condition, initial point, if I feed it to f, I have an output here. But once I have an output, I can look at all the other points in M that are sent to this point under f. This is the level set. Okay? I'm not going to draw the whole level set, and in fact, I'm not going to draw most of it. Let's say, but all I know is that this level set has to pass through this x. Maybe let me just draw it like this. Imagine, of course, in principle, you should be able to draw this, and if the function is given to you and stuff. But imagine that you can't actually see it. What you want to do is, well, you want to figure out how it looks like. In a sense, you should think of it like this. Being able to see the level set f equals f of x near x is essentially equivalent to being able to write down phi, or having at hand the phi function. You should think of shapes visible to you insofar as they are graphs of functions. Okay, that's sort of the appropriate heuristic in this case. So you want to figure out this shape. You take a nearby point, x1 bar. Now you initialize an arbitrary height, x2 bar. It has to be close enough, of course, but let's say it's somewhere here. Different color. Let's use red, actually. And then orange. OK. So you initiate. You say, this is my first guess. Let's say I'm guessing that the function, so the graph of the function that I'm looking for, passes through this point. Maybe it does, maybe it doesn't. Okay? If you're lucky, it is, in fact, passing through this point, and you're done. If not, what do you do? Well, you say, oh, I should have said, perhaps, the height here is x2 bar. Well, I can take this point. This is x1 bar, x2 bar. Feed it to f. That's going to give me an output here. Okay? Take this guess. Apply f to it. It's going to give you something. If this output hits exactly the target output, you're done. That is already in the graph that you want. If not, that means that there's a discrepancy. Okay? Based on this discrepancy, you're going to update your guess. Take this discrepancy. It's over here. Bring it back so that it's a vertical vector now. That's applying this, the inverse of the vertical derivative does that to you. Okay? You take the error in the outputs, you bring it back to a vertical correction. Then you take your guess, correct it based on this vertical correction this gives you. Okay? And so now that means that applying k sub x1 bar to this guess is a better guess as to where this graph is passing. So maybe once you apply this k, it goes here. Okay? So now this point is x1 bar, comma, x1 bar, k sub x1 bar applied to x2 bar. The point is that based on the construction, this target point you want to get is a fixed point of this contraction K. So you want to keep iterating this procedure, and asymptotically, you're going to converge to the right point. Okay? So that means that once you fix this x1 bar, K sub x1 bar is going to act as a contraction on this slice. It's going to contract everything to the correct point. And where it contracts everything to is where phi of x1 bar should be. Okay? But then again, not only do you want this to work for only k1 bar, but you want it to work for any nearby point. But BCP tells you that essentially, based on how we defined it, to each slice you get to do this, and as you vary x1 bar continuously, this height varies continuously as well. That is another way of saying that this phi is continuous. That was the end of step 2 in the proof. But then that requires further arguments to show that phi is in fact differentiable and so on. Okay? Any questions about this? You fix a horizontal component, you feed it to your k function, or you initialize at some arbitrary height, you apply your k function to it, gives you some other height, and asymptotically, if you keep iterating this, it's going to converge to the correct point. Just to clarify, so you're not done, right? So you sort of like keep iterating until you reach the correct point. And so maybe I should do this. So if you start with an x2 bar, in the next iteration, this is a new height at x1 bar. Then you look at, again, the discrepancy with the output. That gives you a vector. Bring it back using the inverse of the second partial. Update your guess again, which means that you apply this to this. That is to say, k sub x1 bar to the 2, you're applying twice to your initial guess. Okay, now this is going to get ugly, as you can imagine. So minus e2f. Let me just write it out like this. But then you would need to open this up, and then this up, and so on. Ultimately, we're going to have that phi of x1 bar, purely based on Banach Contraction Principle, is nothing but the limit of this as n goes to infinity. Here's a very nice exercise. Open these up as well and come up with a nice formula for the nth iterate. By doing that, you can actually write, you can actually come up with a formula for phi as a power series. It's a very nice exercise. I did this just before, but let me think. I think it's something like this. Yes. This one bar. And one more, x2 minus f of x. Okay. What is nice is that this is a geometric series, converges exponentially. That's a formula to the solution. Now, it's a different matter whether or not you can actually compute this, but at the very least, you can say, I'm just going to iterate this formula 5 times, 7 times, however much compute you have. On the other hand, too, just to give you 2 more comments about this, when you think about this, this is basically, at a very high level, the same thing as what a neural network does. A neural network, it ultimately, to express things, composes linear functions with nonlinear functions. Takes one linear and then one nonlinear, and so on. And here too, when you look at this, even at the first step, you have an x2, you apply a nonlinear function to it, and then a linear function. But then, to get the actual solution, you take this, feed it back into it. Okay? So somehow, applying linears and nonlinears together in series gives you enough expressivity, in a sense. Now, in neural networks, there are all these theorems, like universal, what is it called? Universal something. Universal approximation properties and stuff. Essentially, if your neural network algorithm or architecture is sufficiently complicated, you can express pretty much everything to an arbitrary degree. That doesn't mean you should, but at the very least, from a technical point of view, it's not impossible. Okay? Any questions or comments about these? One final comment I want to make about this is that if you have more compute, in fact, you can change this k function just a little bit. And you would then perhaps escape this BCP paradigm. But there's a different paradigm that is related, which is what is called the Newton method. So there's a paradigm, for instance, there's an algorithm that allows you to find the zeros of a polynomial. You start with a guess, and using the derivative, you can sort of again, iterate, and it converges to the root you want. And so if you want to do something like that, Newton method. Now, this is more expensive. Instead of using always a linear operator at this fixed point, at each step, you update the linear operator also. Now, this is more expensive because you need to compute derivatives at infinitely many points, but it converges faster. But there are certain technical issues that one needs to be careful about. OK. Gets more technical, more complicated, because we cannot just use BCP this time because we're not iterating the same function over and over. Every time the function itself changes. But this is something people do. OK, this is all I wanted to say about, in fact, differential calculus. So now we can talk a little bit about integral calculus, unless you have any questions or comments about any of this. Yes?
You have the expansion for x2 bar minus and then that for the BCP contraction. Was how that works to converge to the level set covered in the lecture? I was like, or what do you mind covering?
Well, I mean, think of it like this, okay? So this was your original guess. Based on this thing, you're updating it. Either you're adding or subtracting, at least in this case. But the point is that we didn't show this, but ultimately for fixed k1 bar, fixed x1 bar, this is a contraction. Which means, based on this BCP principle stuff, it's going to converge to something. But then we also showed yesterday, well, we discussed how it converges to a fixed point for k sub x1 bar, and a fixed point for k sub x1 bar is equivalent to a solution to the implicit function problem. Yeah, the magic is figuring out that you can put implicit function problem into this paradigm. You can sort of import it here.
Was there an explanation of like how that big derivatives term does that? Like it approaches how that second derivative times. I think you briefly covered it.
Well, I mean, think of it like this, okay? So this was a definition. Then I fed this thing into itself. So in this formula, I replaced all instances of x2 bar with this to get this, okay?
Yeah.
But then if I were to open these up, I'm going to get, for instance, here x2 bar minus this linear applied to f minus f. But then I have two linear operators, two of the same operators applied to two vectors, so I can combine them to get this, ultimately. So the formula for this term is nothing but this formula, except that instead of the infinite sum, you have a finite sum up to degree n.
I think I get how you put it together, but I'm just wondering, like, for a single step, how do we show that it is getting better?
Well, it's based on one of the estimates coming from BCP.
Okay, it'll just follow.
Yeah, I'm just black boxing a lot of things here. Yes. Yes.
I'll review the slides.
Yeah.
Thank you.
And this BCP stuff is not complicated compared to many other things that we discussed in this class. I decided to not discuss it any further due to time constraints.
Sure.
Okay. Yeah. It is within your reach. In fact, it was within your reach, like before we started differential calculus. Has nothing to do with differential calculus, these estimates or whatever. Okay. Any other questions? And so this was an exercise. Okay, integral calculus. Let me first remind you integration in 1D a little bit. Also, on Canvas, I uploaded a blurb, let's say, by Terence Tao about integration. And I would, at this point, highly recommend that you, if you haven't taken 3210 from me, or even if you did, perhaps, go back to my lectures and review some of these ideas. But ultimately, when people talk about integration, say in a single variable course, single variable calculus course, they mean, depending on the context, three different things. Maybe more than three, but depending on how you count. See how I want to do this. Let's just first focus on proper integrals. Maybe I should have split it like this. There's these proper integrals, improper integrals. What is the distinction between these two things? Well, proper integrals are sort of like the basic paradigm where you develop the proofs and stuff. Proper integration, proper Riemann integrals is when the function in question has a graph that is in a bounded rectangle. So there is no funny business going on. Bounded function that doesn't go to infinity either vertically or horizontally. Like this. Improper is when you have asymptotics. Okay. Maybe it goes this way, or maybe the function is unbounded, maybe it's both. Okay. So imagine things like 0 to infinity, 1 over x. Now this doesn't converge, of course. Now this does, right? So that's an improper integral. But you've taken 30 to 10, and depending on, independent of who you've taken it from, you've seen how you develop the proper integration theory. You want to start with a bounded function on a closed and bounded interval, and you want to do things, right? You want to have a lower estimate, upper estimate, and so on. But these three different senses of integration go like this. One of them is indefinite integral. Okay. The other one is definite and signed. And the third one is definite and unsigned. Indefinite integral is something like this. You often see these kind of things in differential equations. You have sort of like a function, and you say, oh, this integral f, but then plus a constant c. That constant c has to be determined somehow. Okay. Definite integral, definite unsigned integral is, well, maybe from a physical point of view, you could imagine something like, if I have a density function for a physical rod, I should be able to integrate that density to come up with its mass. Okay? So an unsigned definite integral is something like a mass. Meaning, if, let's say, this is your rod, and your density function is like this, well, it shouldn't matter in which direction you integrate, from here to there or from here to there. The mass should be the same. That's why it's called unsigned. On the other hand, signed and definite integrals, they're more like, from a physical point of view, work. For instance, if you have, again, velocity function, even in 1D, either you're going that way or this way. When you integrate velocity, you get back position. In other words, you really get displacement. There's a difference between going this way with a certain velocity. You have now positive displacement insofar as you assume that that direction is positive. And there's a difference between going essentially with the same speed in the opposite direction. So now the order matters. When the order matters, that's signed integral. Okay? In terms of symbols, when I was teaching 30 to 10, if we're taking integrals of a function from, let's say, lambda to rho, this I denoted by something like this to signify that the direction of the interval doesn't matter. And this I denoted by the more common symbol from lambda to rho. Okay. When it comes to the signed integral, this notation allows you to flip the direction. And so you get to write rho here, the wrong point, and here lambda. But then you pick up a minus. Okay. So for signed integral, the direction in which you take the integral matters. For the unsigned, it doesn't matter. Okay. This becomes an important thing, for instance, when you're doing a u substitution. If u prime gives you a minus sign, do you change the sign of the integral or no? Okay. Well, it depends on which type of integration you're actually using at that point. Now, essentially, the same idea, same triple, same trichotomy, let's say, works in multivariable calculus. But perhaps all of these ideas have different incarnations, even within the paradigm of Riemann integration. Indefinite integrals, or antiderivatives, turn into things like solutions of differential equations or integrability of systems. There's something called integrable systems. Or you can hear things like foliations. Okay? These are different sort of multivariable ideas that are basically the same thing as indefinite integrals. So maybe I should be a little bit more careful with my board work. This turns into solutions of differential equations, integrable systems, integrals of integrable systems, foliations, many other things. What you've spent a lot of time in 3210 was developing this and ultimately this as well. When you develop the theory, this is the thing that you develop first, and then you define signed integrals based on unsigned integrals, because now all you need to do is, well, you need to keep track of what is called orientation. Okay? It turns out that in multivariable 2, insofar as you're looking at functions defined on subsets, let's say R, defined on subsets taking real values, the theory of definite unsigned integrals work pretty much verbatim. There are certain technical issues that we'll get to, but it's mostly fine. Verbatim. as in 1D, definite signed integrals become a bigger problem, because in 1D, the domain of integration is a closed and bounded interval, and you can only go this way or that way. Okay? When it comes to multivariable calculus, first of all, we have the problem of what is a nice set over which we should try integrating things. But even beyond that, how do you make sense of this orientation business? And how should the integrals change as you switch the orientation? In 1D, when you switch the orientation, you only pick up a minus. In multivariable, essentially this is also true, but orienting things become harder. And a final thing, too, is that ultimately we want these integrations so that the fundamental theorem of calculus works. Meaning, we want something like this. Right? Now the orientation matters here. What is this? Based on the fundamental theorem of calculus, it is f of this minus this. It doesn't matter. In fact, I should write it perhaps like this. Alpha beta. It doesn't matter if alpha is to the right of beta or not. This is always f of beta minus f of alpha. Okay? So somehow we need to develop this signed integration theory so that something like that still works. Next week, we're going to be focusing on this. And then the final part of this class is going to be all about this definite signed integral. And this is where differential forms come into play. OK, I'm out of time. Thank you. We're done with differential calculus. Tomorrow, we'll do a review.